Long before the invention of the microchip, Plato imagined humanity as prisoners chained in a cave, mistaking shadows on a wall for absolute reality. Today, as rendering engines build increasingly seamless digital worlds, that ancient thought experiment has resurfaced as an engineering problem. In 2003, Oxford philosopher Nick Bostrom formalized this anxiety into what he called the simulation trilemma. The logic relies on a statistical probability. If any civilization eventually survives long enough to develop immense computing power, and they choose to run highly detailed ancestor simulations, the number of simulated conscious minds would rapidly dwarf the number of biological ones. Statistically, the odds of being the original physical civilization drop to nearly zero. Philosophically, it forms an airtight loop, but philosophy operates independently of physics. If our universe is an engineered construct, it has to run on a physical substrate, and physical hardware always leaves a measurable signature. To find out if we exist inside a program, physicists treat the laws of nature as software constraints and the dimensions of space as hard-coded hardware limits. This approach draws on the foundational work of American theoretical physicist John Archibald Wheeler. Wheeler summarized his perspective with the phrase "it from bit." He proposed that every particle, every field of force, and space-time itself derives its existence from the answers to binary yes or no questions. Decades earlier, computing pioneer Konrad Zuse suggested that the universe functions like a cellular automaton, a vast, discrete grid where every localized cell sequentially updates its state based on rigid deterministic rules. Treating the cosmos as a self-contained information processing system is a mathematically robust way to study physics. Proving that an external entity artificially programmed those rules, however, requires stepping outside theory and hunting for physical glitches in the cosmos. If space is rendered by a computer, it cannot be perfectly continuous. It must have a minimum indivisible unit of resolution. In physics, this is known as the Planck length, the smallest measurable scale before current theories of gravity break down. When physicists try to simulate the strong nuclear force on supercomputers, they use a technique called lattice QCD. They divide continuous spacetime into a rigid three-dimensional grid to make the calculations manageable. Physicist Silas Bean suggested that if our universe is running on a similar discrete lattice, the grid itself would impose a strict rendering speed limit on the highest energy particles. Astrophysics recognizes the GZK cutoff. When ultra-high energy cosmic rays tattle through space, they lose energy, establishing a natural velocity cap. If this is a computational artifact, those rays wouldn't scatter randomly. They'd travel preferentially along the lattice's intersecting axes, breaking rotational symmetry. Researchers analyze millions of atmospheric collisions recorded by cosmic wave detectors on Earth, searching for these specific directional biases. The data shows no preference. High-energy particles arrive in a perfectly isotropic distribution from all directions. The fabric of space appears entirely smooth, yielding zero evidence of an underlying digital architecture. Commercial video games conserve memory through lazy rendering. Instead of generating the entire virtual world at once, the engine only computes the exact details of an environment when a player turns to look at it. Proponents of the simulation hypothesis compare this to the quantum measurement problem. A quantum system remains in a probability wave until an act of observation forces it to resolve into a definite state. Physics also enforces strict data limits. The Bekenstein-Hawking bound dictates the absolute maximum amount of information that can be contained within any bounded region of space. Treating quantum mechanics as a resource-saving algorithm fails when dealing with quantum entanglement. When two particles become entangled, their states are instantaneously correlated, regardless of the physical distance between them. Simulating this requires tracking non-local interactions across an exponentially growing number of variables. Under the many worlds interpretation of quantum mechanics, the problem scales to infinity. Every quantum event branches reality into separate, persistent outcomes, forcing a computer to track every possible historical path simultaneously. The processing power required to calculate the entangled states of just a few hundred particles exceeds the total number of atoms in the observable universe. A classical computer capable of running this simulation cannot exist within the physical limits we observe. There is a stronger objection to a simulated reality. The universe contains physical phenomena that appear entirely resistant to computation. In 1931, logician Kurt Gödel published his incompleteness theorem. He proved that any sufficiently complex mathematical system will always contain true statements that cannot be proven using the system's own algorithmic rules. Theoretical physicist Roger Penrose applies this logic directly to human consciousness. Since humans can understand mathematical truths that algorithms cannot prove, Penrose argues that the human mind cannot be operating on a purely mechanical, rule-following procedure. Penrose locates this non-computatable process in quantum wave function collapse within the brain. He views this collapse not as a calculation, but as a spontaneous physical event that falls entirely outside algorithmic prediction. If human understanding requires non-computable physics, then the universe cannot be a conventional software program. A standard computer simulation cannot generate an output that exceeds the boundaries of its own code. Physicist Sabine Hossenfelder draws a strict line between studying the informational nature of the universe and engaging in pseudoscience. Applying information theory to thermodynamics, quantum mechanics, and gravity is a legitimate, rigorous pursuit. The universe processes information. Proposing an external programmer, a being existing outside our physical laws who can selectively bend them, pushes the hypothesis entirely outside the realm of testability. We have searched the highest energy scales and found no rendering grids. We have tested quantum systems and found computational demands that exceed the capacity of matter. The simulation hypothesis offers an intriguing thought experiment, but deciphering the authentic laws of nature remains humanity's actual pursuit.